Taylor Satterfield.
Hi, I'm Brooke Paget, and we're going to talk to you today about the Search for Non-Interacting Particles experiment. So first we're going to talk about what dark matter is and what the project is all about. Then we're going to tell you what specifically we did over winter term. We're going to do some reflections and acknowledging people, and then we're taking some questions, okay? So what is dark matter? Well, first of all, this is the standard model. It describes all of the particles that we know to make up our matter. But dark matter isn't any of these particles. And dark matter is actually very weakly interacting with these particles, so it makes it hard to be able to see it. So if a dog right now made completely of dark matter walked in, we wouldn't notice. We wouldn't hear it bark, we wouldn't hear it go up to Desi because she loves dogs so much. We wouldn't even notice because we don't interact with that matter. Well, I just told you that the particles we know of don't make up dark matter. So what particles do? That's a complicated question. There's lots of different hypotheses out there. But we're going to focus on two dark matter candidates: hidden photons, which are also called dark photons, and axions. And what's special about these two is they have very weak interactions using gravity, but we can also detect them using magnetic fields. And even fun fact, axions were actually created to solve a whole different issue in physics. And even more fun, if you take even one physics class, you'll notice that physicists aren't very good at naming things. And this is the perfect example because it's named after a type of dish soap. Like literally, they named it after dish soap. So how are we trying to detect these hidden photons and these axions? Well, these hidden photons and axions can be converted into a magnetic field. So basically the Earth itself is conductive, and then this pink ring around it is also conductive. This is the ionosphere. And these hidden photons and axions can generate a magnetic field, which are denoted by these yellow arrows. And we can try to detect this magnetic field. So what are we using to try to detect them? Well, we're using induction coil magnetometers. That sounds really scary. Magnetometers just means that it's something that detects magnetic fields, and induction coils are just the type of magnetometers that we're using. So this is the core. It's about 12 pounds, and it's made of mu metal, which is mainly iron. And then we wrap copper wire around it, which makes it even heavier. And then these are what we use to actually detect magnetic fields. So where are we doing this? Well, we have 3 places that detect magnetic fields. We have California East Bay, we're over here in Ohio, and then Bucknell University. Well, so these induction coil magnetometers, they read all magnetic fields. They don't just pick the dark matter ones. And this can become quite an issue because lots of things give off magnetic fields. Your phones, the lights, the metal in your chairs, they mess with the coils. So how do we get around this? You go camping in the middle of nowhere, like with actual, like this is real camping, guys. Like not glamping, no Airbnb. So this is the Cal State East Bay group, Oberlin, and then the Bucknell University group. And this is from the first camping trip we went on. And we set up these detectors out in the actual wild. And then for 5 days, we take data and then we analyze it all. Well, there's one big kind of caveat to these coils, is they're just made down in the basement by the machinist Mike Miller. And there's no equation where you can just say like the length or like how wide it is and get the sensitivity of the coil out. That's not a thing. So we have to figure out some other way to find out how good our coils are actually. So this is the noise from the first coil, and then the second coil, and then we subtract them and we see some noise and stuff, but this actually doesn't really tell us that much. But we're trying to actually characterize these coils, and that's what we did over winter term.
So our winter term project was primarily held in the classroom, and our setup consisted of 2 induction coil magnetometers, which is magnetometers, a data logger, and a computer. So the magnetometers takes a magnetic field of everything around it, and the data logger interprets that and puts it in time, and then we need to use the computer and resources in the computer to convert it back to magnetic field. And as said earlier, the reason we have 2 magnetometers is because since we're working inside of a classroom, we have a lot of noise from the building, from the computers and everything, surrounding noise. And however, since we have 2 magnetometers, so it should be roughly the same, they should be taking in roughly the same amount of noise noise in the surroundings. So when we get our final data, we'll be able to cancel out that excess noise and just be left with the magnetic field of the magnetometer itself, which will help us tell us how sensitive they are and what we need to do to improve the coils further. And here's a picture of our set in the classroom. You can see the magnetometers we use, the whiteboard that we use to hold them in place. The red circular object is our data logger, and this is our computer. And on the computer, you can actually see the data that is coming straight from the data logger when we first take it. And now I'll give you a presentation of our oscilloscope. So our oscilloscope is very important because it lets us know if anything is messing with the magnetometer in any way. Right now, without any interruptions, you can see there's constant waves. This is pretty good. However, if I simply take the magnetometer and I push it back and forth, now you can see that it's not happy. A lot of something is interrupting. If I stop, it goes up to normal. This tells us that we need to make sure magnetometers are in a secure position. They can't be on any unstable material, and they themselves certainly cannot move either. Now, if I don't touch the magnetometer, I just take this iron board, I move it around it as well, it's also not happening. This tells us something too. It tells us that we need to make sure our workspace is clean. We can't have anything rolling around it or in between magnetometers as we work, because that can make us record inaccurate data. With that, I'll get back to the slides. So this is a still version of the oscilloscope I showed you earlier. And in these pictures, you can see two graphs, a blue graph and a yellow graph. Each color represents a different magnetometer. Now we're still on the right side over here. The top one is not a good graph. It's not a good graph because you can see flat lines on the top and bottom. And that is telling us that the magnetometer itself is in an incorrect position. Incorrect position most literally means it's vertical instead of horizontal, like it's facing the wrong way. And the reason that can interfere so much is because the magnetic field inside the building is so large that the magnetometer is not in the right position, then the information that the data logger takes in will be too much for it to handle. And then it'll just flatline instead of reporting it, which will have us record inaccurate data. The bottom picture is also not good. It is technological noise. We actually got this by putting our phones directly on top of the magnetometer, which creates a lot of this fuzzy stuff. And so to prevent that, it's really key to have, again, like I said, a clean workspace. Can't have any technology, no phones, no computers. Just have it clean. And we'll get into the best possible outcome now. This is the best possible outcome. You can see no flat lines, not a lot of fuzzy. You can read it pretty accurately. We call it best possible outcome though because we are still inside of a classroom. So compared to if we were to go camping, this is relatively noisy. But in the environment we're in, this is the best possible outcome we like to see. Now I'll talk about a resource we use to help us get our data further. Mathematica is like our translator, if you will. It helps us read our graphs better. So this is like our raw data that comes straight from the data logger. It's extremely important, but we can't really read it well. Because if you see, it's just data. You can't see a trend, you can't see any real peaks or troughs through. It's just data. So we use Mathematica to put it in frequency, for example. Now with frequency, this is much easier to read. We have clear peaks and clear troughs, and we also have a general trend we could not see in the first graph. So Mathematica just helps us read our data better. This is really fun. So actually we created these holders in the student workshop in the bottom of the physics building. And they're made out of PVC boards, which is a strong white material that I have in front of me. So we first use a bandsaw to actually make the rectangular shape that you see here. Then we use a milling machine to smooth out the side that we sawed. And then we use the hole saw to make identical holes for the magnetometers.
So, this is my first Mathematica crash. It was a horrible, horrible day. I was given a simple task. I crashed the whole system. Then it did this it was crazy. And then now I crash Mathematica like 5 times a day. It's a lot. But I had so much fun over winter term. I feel really passionate about this project. You know, it's just like, it's all those little boxes in my brain, and it's just amazing. And I'm really excited to continue working in SNIPE and trying to detect dark matter.
I had a lovely time doing with this winter term. All these pictures were like on the first day. This is my first Mathematica crash. As you can see, a very different reaction. I think that just happened. This is my first Mathematica graph. And this was just like the first day setup. I was completely in awe. Like, I never saw any, I didn't know what a oscilloscope was. I kept calling it an oscillator for some reason. I was mesmerized by all the equations and like the circuits and everything that was happening within the lab. But overall, the lab was extremely welcoming. And I was really excited and really happy I'm able to complete this project with all of you, Professor Stone and Kirkbrooke, in the lab. It was great.
So what's up next for SNIPE? Well, we found out very much at the end that this little red box we use to help us collect the data actually produces a lot of noise. So now we have to design a new one, which I think is going to be a lot of fun. Professor Stalnaker is kind of not feeling that. I think it's going to be fun. And then this summer, or for the rest of the semester, we should hopefully make some new, more sensitive coils. And then this summer, we'll be back camping again. So we would like to thank Professor Stalnaker, of course. He was so welcoming and let us ask so many questions and never judged us for these questions. One time we were doing something with this equation and there was this variable in it that, you know, he was like, oh, you know, I think this is going to be 0, so we don't have to worry about it. And I go, you think? Like, what makes you just able to think that? And he goes, my 30 years of being a physicist. And I was like, oh. But then he explained it, and turns out he was right. But I really liked seeing that process of, you know, why we were just able to call this variable 0. But he was really welcoming, let us ask so many questions, and just amazing to work under.
I want to thank Abby and Clea. Thank you so much for just helping all of us through this winter term. It was lovely. Your comments were amazing. They really helped me brush up on my slides and all my other things winter term. So thank you both.
And we would like to thank Josh and Anya. They are 2 upperclassmen working on GNOME, which is like the older sibling project to SNIPE. And they were so nice. They treated us to pizza once. It was amazing. They're gonna do like amazing things that I'm not gonna understand because they're just like way too smart for me, but they're so nice. And thank you so much for welcoming us so much. Are there any questions?